All right, our next speaker is Mike Himbeault. Very easy.
Thanks, Ron. So Paul set me up for failure. I mean, it's the relationship we have. So imposter syndrome here. If there's anything on any of these slides that you know that is I'm either probably not going to talk about or I'm going to miss or that you think is super cool, just like point at me, because it's important for all of us to recognize that the people up here don't know everything. And I put 11 hours into this, not 11 years. There are people who've put years into this topic. So, and all the parts that go into it. So if there's something that you know that's super cool, find me out there or ask it in the question period. But like, it should be known that there's folks here that know a lot more than me. This is not going to be about a deep dive into what Kubernetes is. I'm going to talk surprisingly little about Kubernetes. And I'm also not going to boil the ocean. It's going to kind of seem like it, but I've sort of picked and chosen the path I took through history to get here. And I've missed a lot. There's a lot of stuff that went on that was really important, that was foundational for something else and was tangential to this, and I just kind of skipped it. It was all like there was tons of cool stuff I wanted to talk about, it just wouldn't have fit. So educate the room, ask, mention it later, or come find me. So this is a story of wanderlusts. Like this is a story for adventure, for growth, and for the kinds of decisions you have to work really hard to make. And not just do that, but make them over and over. And it's going to be hilarious. So just to explain Kubernetes, I asked GPT, so I'm just going to read it. It does a fine job. It's a platform for managing containerized applications across a cluster of nodes. It automates the deployment, scaling, maintenance of these applications, provides features such as service discovery, load balancing, storage orchestration, self-healing. Kubernetes is based on Google's experience with Borg. Is that trademarked? By who owns the Star Trek franchise? I don't know. And is open source and extensible. That part is awful. We're going to come to why that's a problem. Kubernetes is widely used for cloud native and hybrid cloud workloads and has a large and growing ecosystem of tools and services. Great. Fun fact, most of those are configuration based and half of those are Turing complete. The configurations are Turing complete. You can execute arbitrary code in Kubernetes configurations without running any workloads on Kubernetes. So we'll just think about that one. So let's talk about SharePoint. So who's familiar with the inter-platform effect? A couple of people. One, because I told you about it. So the inter-platform effect, in horrible language, is basically when you attempt to implement something so general and so generic that you re-implement the language you implemented your thing in. Just worse in every conceivable way. So SharePoint is an application server that comes with storage out of the box. Salesforce is an application server that comes with contact management out of the box. Kubernetes is state management backplane that comes with container management out of the box. You could, if you wanted, using custom resource definitions for Kubernetes, implement the life cycle of a human and vital statistics tracking without ever running a container, except those required to run your Kubernetes object structures. That's realistically what it is. It's not something special or new. It takes things that we've done half a dozen times sometimes. So we're going to start with some questions. Virtualization. What virtualization tech won? Does anybody have an opinion on this? I mean, I'm asking cold, so probably not, but think about it. Who likes Kubernetes? I mean, like, really likes it, like, would bring it home to meet your parents. Right? Okay. We may have to reevaluate friendship. So there are two kinds of multitasking, and we've come up with them both. There's bad and there's worse. And the last one, who had a computer before a 386 and then got a 386 after that? Okay, a handful. What did you think of the 386? Right? Right? We're going to talk about why that was and why that relates to Kubernetes. So we're going to go through a bit of a Build-A-Bear workshop. Right? The insides are made out of real bear sometimes. And we're going to start with the history of processes. So I should probably start my timer. That's fun. Awesome. Cool. So back when IBM was cool, they were working on this thing called the IBM System 360, which was their whole brand new mainframe, and we just got transistors. Vacuum tubes were no longer cool, they were hot, and transistors were better, so we started doing that. And you could do tons of stuff with them that we couldn't really do effectively before. And on top of this, they built the System 370, which on top of that, they built VM 370, which is where they allowed you to re-implement a previous version of their mainframe as a process on their new mainframe. This was our first virtual machine. You could run CPCMS as a process inside of a System 370, because that was a thing that tons of people wanted to do, and transistors let you do a bunch of that. So that was sort of our first foray into all of this. If you don't like it, if you don't like that I'm saying IBM is cool, you're not going to like the rest of this, so stick around. Rage bait is how I get audience engagement. So 1971, right? It's not Unix, it's Unix, just so we're clear. And multi-session time sharing is the new hotness. Like this is how people are doing mainframes, it's how they're doing business. And it's sort of the first time we get computing experiences we'd recognize today. There's a terminal, it connects to a thing, and it does things, and a bunch of people can do the things. It's green on black, which I think 50% of the crowd probably prefers. White on black is the new thing, but that's generally where we ended up at this point in time. And then 11 years happens, and nothing happens. 11 years goes by. And then we get 2 years before George Orwell's seminal work on how to build a utopia, we get the 8286, which makes an attempt at what VM 370 did. So before the 286, you had the initial, like the 8086, like the initial x86, the first one, and you could do real mode. That was it. It was one process, or I guess you could maybe fit a couple, and they had access to everything. There was no sandboxing. They could clobber each other all day long and just fight it out. It introduced protected mode. So this is a super important development because it's been on mainframes and it's finally something that you've got on a consumer device where you can segment and separate different processes. Most operating systems don't let you run more than one yet, but you can start to separate them out logically. Now it's broken, it doesn't actually function at this point in time, so that's fine. But it sort of marks the key point where we've all agreed that this is a thing we want everywhere. So let's start miniaturizing it. 1985, virtual memory comes with the 386, right? And now we have VM 86 because virtual memory finally actually works. And now you can actually run all those things you had on your original 86 computers, and you can run a bunch of them, and they don't clobber each other anymore. So we should talk a little bit about how that works. So we're going to do sidebar, real mode, protected mode, and VM86. Again, this is stuff that lots of people know tons more than me on, but we're gonna do a real quick sort of shallow dive in them. Naive computing is real mode. Like you've got one thing, it's got access to all the stuff, it's just pseudo everywhere. It's giving your container access to privileged everything, and it can clobber anything it wants. This naturally doesn't let you multitask. Don't give your containers in Kubernetes privileged access. It's bad. We realized it was bad in the 80s. Don't do it in the 2000s. Protected mode tries to fix a lot of that, right? It lets you sandbox memory. It gates access to shared resources, disks, peripherals. I guess technically network. Let's call it a peripheral. It's a really slow mouse. And it gates them all through a manager. So it traps the calls and then passes, hey, this protected process tried to do a thing. What do you want to do about that? You're this one's parent. Here's your child. What do you want to do about this? How do you want to handle it? The first one just didn't work because it didn't work right. Everything got confused. Direct access didn't work. And it was just this horrible cycle of sadness. So VM86 introduced that whole concept of a virtual machine manager. So it was expose all functions in protected mode, so things look normal, But as soon as something tries to use a protected function, you trap it. And then you hand that trap over to a parent process, a manager. And then you can actually choose what you want to do with it. You can abstract it, you can grant direct access, you can grant only one process access to a resource or a peripheral, you can share it, but you get to decide in software how you handle these resources and how you abstract them. 92, one of my coolest bios. 92? 92? Yeah, sure. Anyway, preemptive multitasking. So right, remember we had bad and worse multitasking? So there was cooperative, where everyone has to agree that we're going to hand off to each other. And preemptive multitasking finally shows up. It comes out in waves. Sun OS, Solaris has it. Windows 3.1 has protected mode. In protected mode, has some amount of preemptive multitasking, which is cool. Mac still sucks. Linux doesn't exist yet, but Unix has always been preemptive. And building on the work from like mainframes, Motorola, like the Amiga had this weird little thing where you could do with it, and it kind of worked. But this was really when we started to see this new thing. So now we can segment our processes out, but it's not effective for switching between them yet. So what made the Pentium special? Right? So, shit, how did that get there? All right. The problem we were having with the earlier processors is that you had to do weird stuff like memory mapping unit shadowing, because your internal processes kind of wanted to manage their own memory, and so you were managing it, and you were having all sorts of issues come up. It was a superscaler. Super fun question. When did we get compare exchange, before or after we had dual core CPUs? We got compare exchange with the Pentium, because you had superscaler. So you could be unloading the dishwasher with two hands, and if you have a cup and a plate, that's fine. But if you have two cups, you now have to decide where you're going to put your two cups. So we actually got compare exchange with the Pentium, which this is something I learned, and I thought that was really slick. Why was Windows NT special? Windows NT is special because it had full preemption in some modes. So we finally have an operating system that's reliable because it doesn't depend on processes. All those virtual processes we can now support in hardware, it doesn't rely on them cooperating. So if one of them goes rogue, we don't have to worry too much about it. We can just, it still gets scheduled and then descheduled like everything else. So there's page table mapping, there's all sorts of fun stuff that happens, all in 1993. It's a pretty cool year. Spot the pattern. Why was Windows 95 so good? It was consumer preemption for everything. Kernels, drivers, user space. So it was, why did it seem more stable than everything else before it? Because nothing on it had to cooperate. Nothing on it had to be special. So when we're looking at how all of our processes, and keep in mind, when we talk about processes, you can form a direct in your head translation, just like Travis suggested, just read containers now, right? Like if you've got something that if you're running on Kubernetes, you don't give a CPU limit for, well, it will suck up every part of the CPU on that host if you let it that isn't reserved for something else there. That is not cooperative, but that's how people deploy Kubernetes. That is the default in most Helm charts, is there is no resource limits. You just go kubectl apply, and then something goes rogue and everything is busy and nothing works. So Windows 95 is pretty slick because we finally got that. Mac would need a while still. Bonus points if you can guess when. So it has, but only because it stole it. I mean, it didn't steal it. It was technically legal, but that doesn't make it better. Anyway, so late 90s, VMware and a couple of others, but I'm just like VMware is a critical part of this. Full virtualization is going full tilt now. So they've got VMware Desktop, VMware Server comes out in a little bit, but they take that whole trap and translate approach that we'd used with the VM86 at this point 30 years ago? 20 years ago? 20. And they do it in software. So they do a super slick thing called full virtualization, which is different from para-virtualization, which is different from hardware-assisted, which is just full or para-virtualization with some hardware hacks. But they simulate everything, and then they trap problematic instructions. Problem is, you can't do that at this point on hardware in 86. There are tons of instructions that do not trap, but will pierce or peer through that VM layer. So if I'm going to go and write to disk, that's a shared resource that all of these virtual machines that they want to run, all of our pods, all of our whatever, anyone can write and read from that disk. It's a shared state. Or if I want to look at the state of a peripheral, I can see what privilege level I have. So I'm either piercing or peering through that virtualization barrier. So they did this really slick thing where since x86 has so many instructions, it's been such an iterative garbage show for so long that there's no such thing as trapping all of them at this point. So what they do is they do binary translation. They take the binary that's executing and they replace parts of it with equivalent instructions that still work in all of the right size code page tables, even in self-modifying situations. And they replace them with either benign or trappable instructions, and then they can do something with it. So that's how full virtualization worked. It was super cool. VMware has a pile of patents about it too. So now let's take that and let's think, well, okay, so that's a lot of work. It's a lot of overhead. It kind of sucks. The performance is terrible because the thing that most things have to do, which is either talk to the network or talk to storage to be a functional tool, well, those all require trapping. So what if we replace those with virtualization-aware components, drivers that knew they were in a virtual situation and would deliberately tell the hypervisor, like the manager, what it was trying to do? Well, that's para-virtualization. That's what PV is you take the parts of it that are super problematic, disk and networking, because those are the ones that everything has to do to be a useful tool, and that's how we got VMware tools. That's what those is. Those is. Great. Look at me go. So that's para-virtualization. It's pretty cool. And then you get full para-virtualization. Well, it's just to the whole operating system. That's how you got the first generation of EC2 on PV instances with Xen and para-virtualized handful of Linux guests. The whole OS kernel was rebuilt to be para-virtualization aware. And thankfully, you could do most of it with just the syscalls and inside the kernel. You didn't need to recompile a ton of user space. But that's what this was. Pretty cool. So let's stick a little bit of a pin in that one, and don't forget what this is. Hardware-assisted virtualization is really saying, what if the hardware trapped for us? All those instructions that we're trying to keep track of that cause problems, what if the hardware actually did it? Like, hardware traps are better. They're not free, but they're better. And that would make PV technically unnecessary, but we still have tons of benefit. Because if we don't have to trap, we just do the thing through those VMware tools, you still get better performance. It's why VMware tools is still a thing you install all over the place. There's a neat thing. I'm going to skim through this slide, but it's useful if you're a super nerd. They talk about how do you build a theorem around what you can virtualize and what you can't. How do you identify which instruction sets and which architectures actually let you do that? It's kind of slick. For example, PowerPC, everything works the same in privileged and unprivileged modes. It's just in an unprivileged mode, it won't work, which is super easy. Like, PowerPC just naturally supports virtualization if you really want it. Spark did kind of the same thing, except they had a separate privileged mode where you could say, oh, by the way, I want you to trap these instructions and tell me when they happen. So Spark built this from the ground up. x86 is just like, fuck it, let's go, right? So they're just like, well, how is this the one we ended up with? I don't get it. It's a terrible idea. And then we keep going. So for the ones that survived Y2K, this was pretty cool. FreeBSD4 adds jails. So finally, chroot is a useful thing. Useful. No one from Securus is here except for Rob. You're fine with me, right? It's fun. It's cool? Okay, we're cool. VMware Server comes out. They made an acquisition, filed some patents. That was slick. But that was just it. At this point, critical patents have been issued related to virtualization. Everyone's favorite topic. Who loves patents? Awesome. Okay, great. So we'll go quick, but VMware has patents for virtual machine management. AMD holds critical ones for IOMMUs, which is hardware we're not going to get for a little while still. But there's tons of interesting ones to Intel around real-time scheduling for all sorts of virtual machine guests. There's GPU hardware page faulting for NVIDIA for things like how do you manage IO mapping for GPUs with more video memory if you have page faults. Storage had a ton of stuff. Like Data Domain has a patent on deduplication. And NetApp has a patent for snapshotable file systems. And NetApp and it was Sun originally and then Oracle, and they were basically just having this huge pissing match for 3 years from 2007 to 2010 over who owned the patent for snapshotable file systems before both just collectively deciding, you know what, never mind, that's fine. So they just agreed to drop everything without prejudice, which means that that's how we ended up with deduplication as such a standard feature. Everyone agreed that, okay, fine, whatever. Nobody owns that one. Isilon has patents for distributed storage with hot spares. VMware has a pretty cool one about VMFS for clustered storage without server-to-server communication. It's all done through the shared storage subsystem, which is why VMFS is technically kind of unique because of this one. VMware patented how do you store a block volume efficiently on a real file system. They got a patent around that one. That's pretty cool. It's how you end up with vvols. It's how you end up with a ton of actually, it's really how overlay storage kind of works within Linux and the Linux kernel. NVIDIA's got one around efficient block devices as file systems, and there's some stuff around networking. So HP Moonshot, I'm not sure if you're familiar, but it's like 256 individual compute cards in a single chassis, all of which are addressable for VDI. Kind of neat, but the networking in there is crazy. It was an interesting time. Linux was not. Linux was boiled garbage in 2.4. So finally in 2.6, it's better. Apple sucks in BSD and Next Step and finally releases the mock kernel and OS X. And in 2001, reaches where Windows 95 was. So if you don't like it when I say IBM was the cool kid, you're going to like it even less when I say Windows is, like Microsoft, was legitimately better in software. Now, they were running at x86, so whatever. PCI SIG ratifies SRIOV. I'm going to go through this one real quick, but SRIOV lets you take one thing and make it two things. And it lets you say, you now get a thing, and you now get a thing. And usually we did this with networking adapters, but you can do it with a ton of stuff. PCI devices they're a hardware function. They perform a function of some kind. They send packets on a wire. They display inappropriate content on your monitor. They do things like that. So how can we make one of those that does that, just do it more than one time? Especially network adapters, right? Like those are so easily multiplexable, this makes sense. So SRIOV is what lets us do that. It basically lets you say through the driver, hey, you over there, I need you to make me 6 more of you, and then map them all to distinct PCI Express address space. And then I'm going to take that distinct PCI Express address space, and I'm going to pass that to someone else, whether that be a process or a container or a virtual machine. That's a PCI Express virtual function, and they're really slick. They're super cool. We've had them originally in would have been probably InfiniBand network adapters if you're in the enterprisey space. I'm assuming the slide deck's going to be available after, so you can read this if you want, but that's the gist of it. So network devices, that's the obvious one. FPGAs, another obvious one. NVIDIA, if you've ever heard of NVIDIA Grid on some of the workstation GPUs where you can have it virtualized, that was super driver assisted. And then with Ampere and the A100, and that made it into all the workstation 3000 series and newer, now it's all SRIOV, like it's all just directly PCI Express devices. It's pretty slick. It works really well. But it's taken us a long time to get here. But this is how you do pretty much every major CNI for Kubernetes works this way. If you're in Amazon and you're using the VPC CNI, that's how it works. If you're using something like Pensando or some enterprisey networking DPU weird garbage like buzzword, that's how it works. It'll split itself into multiple personalities and you hand them directly to containers. That's slick because you can now give a container 100 gig networking. A single container. And then if you've got a 200 or 400 gig card, you can do that to 4 separate containers. And each of them doesn't hit a hypervisor, doesn't hit virtualization at all. It's directly memory mapped from the hardware through right to the containers environment. That's really cool. That's how you can do some of the major stuff that Kubernetes is supposed to enable, not kubectl apply whatever I got from piping curl to sudo bash. That's not what Kubernetes is for. It's not what it's supposed to be for. It's just what I do with it. So 2004, we get Zen. Finally supports PV guests. And we get Solaris Zones, which is jails with actual management. How many people have used Solaris Zones? Great, right? Yeah. I miss it. I so miss it. It's a shame it went away. Technically, it's still there. 2005, we finally get our first generation hardware virtualization. It took us a long time to get here, and we're still not on Kubernetes. I got to speed up. So, and almost instantly, Zen supports hardware virtualization guests. So that's cool. AMD has their hardware virtualization now. And now we have first-gen hardware virtualization, which I mentioned earlier. All it does is trap those things that we care about in hardware and allow us to handle them directly. So now we finally have proper hardware containerization of processes. It's taken us a long time to get here, but this is starting to set the foundation for, oh, segmentation of processes is a thing we want. It's a thing we should do. We're going to use it a whole bunch for full virtual machines because that's what we're used to. But if we think about what this enables, and we step back, not how we've used it, but how we could use it, well, right now I look at this and go, well, this lets me trap every problematic instruction for a process. Why can't my VM just be one process? Why can't it just be Chrome or Excel running that weird macro-enabled spreadsheet from finance, right? Drill.xlsm is not something I want to run willingly, and yet I have to file expenses. This is uncomfortable. So we're here, but the new hotness is everybody's got racks and racks and racks of pizza boxes. We want to consolidate them. So our first shot when we get this is to consolidate pizza boxes. If we could redo this, we'd probably skip that step. We'll come back to that. And Linux 2.6, and this is the other one, adds the mount namespace. Namespaces are a core part of how all containers run on Linux. We got our first one in Linux 2.6. So obviously, when we add a new feature, it's still Linux 2.6. So in 2007, we add C groups to Linux 2.6 because you don't add features unless it's in 2.6. 2008, we get a core hardware feature, which is second-level address translation. So now when you have a full operating system which wants to handle processes in their own protected modes with memory mapping in that operating system, with memory mapping in the hypervisor, and memory mapping on the CPU, that's a lot of translation. And we lost a ton of performance through that. So in 2008, we finally get CPUs that let us do this in hardware, and the performance is significantly better. VTD and RVI are the memory mapping virtualization hardware that we now need as well to go with it. At this point, we've got pretty much everything we need for LXC, except we still can't map a user. So root in a container is still root on the host, which is why if anyone who's been using Docker from the beginning, you don't run the things as root in Docker, that's where that came from. Because when you ran as root in Docker, you ran as root on the host. So a container escape in Nginx running as root was a container escape to root on the host. It's still a terrible idea, but we don't have that exact problem anymore. After 2010, not much happens for hardware. This is the thing. 2013, we finally get a solution to that thing I was talking about. Took 5 years, but now root in containers isn't root on the host. If you're running Nginx as root in a container and someone escapes the container, they escape to some random unprivileged user ID on the host. It's not, you then also need a privilege escalation on the host. So that's a really important part and an understanding I think a lot of people miss in modern Kubernetes and containers, which is it's not as brittle. Like it was mentioned yesterday about brittle detections. We're slowly adding things that make segmenting our processes and things we care about less brittle. Oh, good, I got lots of time. And as soon as we got this mount namespace, Docker, wrapping LXC with management tooling, spot the trend, shows up almost instantly. Like normally it's like wait a little bit, take your time. Docker shows up almost immediately. Best part about standards is having so many to choose from. And my favorite part about what happens next is we start making more of them. So in 2015, Docker splits out and realizes, hey, there's a difference between managing and exposing containers and then running them. They're different. There's different roles and responsibilities. There's different segmentation. There's different, all sorts of different accountability that happens there. And so they split out Containerd from Docker CLI. So now you have different container runtimes. They also found the Open Container Initiative, who then also ratifies the container runtime, the container runtime interface. Hey, I have speaker notes. Those are useful. And Kubernetes 1.0 is released. So like a ton happens here immediately following when we can remap Linux user IDs. Like it took no time at all before we realized that once you fix that problem, you can start to do cool stuff. Great. 2016 was fun because Docker, again, realizes that, wait a second, there's more ways to run containers. So let's not just use LXC, which was a wrapper for C groups and namespaces and was very Linux only. So the OCI releases reference implementations, and Docker Swarm shows up and just splats onto the scene like a wet dog. It's just, who used Docker Swarm and liked it? All right, I'm glad someone is. I never used it. I skipped it intentionally. It's okay, we all make mistakes. Kubernetes 3 shows up and supports these new standards, which is very nice of it. And then rapidly realizes, oh, right, workloads need state. Okay, hold my beer. I got this. Hold my beer. I got this. Wow, that is not showing up at all. Wow. So Kubernetes decides that, you know what, just commit to master. It's fine. Just commit directly to master. It's fine. You don't need storage and networking, but if you do, just commit an in-tree module. We'll just accept them, and in-tree container storage and networking is born. And it takes us a long time to get off of that, almost 7 years to get away from in-tree modules, because CSIs and CNIs for out-of-tree storage end up in beta in Kubernetes 1.11, but then they forgot that people are going to use this to run enterprise applications, which need access to block storage, which is what they've always had access to. How did you forget this? How did you choose to do the thing that no one was doing? No one was just, oh yeah, by the way, your root volume is NFS, it's fine. Like that's not, no, that's not a thing. So they're like, oh right, yeah, so we forgot about that. It's in alpha. I promise it's going to be fine. And then 3 years later, they're like, okay, it's almost okay, but now you have to handle migrating things that have been in production for 5 years. Sorry. And then just walk away from it. So it took us a long time to relearn the lesson that is things need storage and networking. And if we look back at when we got hardware virtualization, the first thing we did was redo the thing that we're already doing everywhere. But because Kubernetes came from Google and their specific use case, that wasn't what they saw people were going to use it for. They think, oh, this is how we use it. Therefore, everyone else will do the same thing that Google does because Google has a large ego. But reality is, you release this technology to the general population, and they're going to see it as an opportunity to do what they're currently doing, but better. And what they're currently doing is VMs and virtual machines of full operating systems. They recognize they're not going to put full operating systems in a container, but they do have workloads that they're going to want to put in containers that have access to direct block storage, or have access to high performance networking, or accelerators, or any of the things that Google just didn't think about. So if there's ever a question around why is Kubernetes such a problem, it comes from the fact that it wasn't built for how we're using it. It was built by Google for Google, and then they released it and went, shit, we forgot. People don't always like us. And then it's been iterating for, what are we on, 28? Kubernetes 1.28? Okay, that's not helpful. So yeah, we've been iterating on it for a long time, and we're almost there. So 2023, Kubernetes can do almost literally anything. Sometimes you have to run a workload. Oftentimes you don't have to if you don't want to. And it's only taken us 63 years to get here from where we started. And we've re-implemented computers 4 times. We've made the same mistakes every time, and we somehow have yet to learn from it. And I don't really understand why. So this is one of those things where, again, we have this inter-platform effect coming up, because each time we get a new piece of technology, we use it to make what we're doing now better. But because we either have a different plan or have the same plan in mind when we build it in such a general way. I mean, just look at how x86 is developed so iteratively that once we finally go and start using it, we end up extending it for a decade or two, its entire lifespan, so that it's so general and so complicated that no one really knows what we're doing. And so someone says, inevitably, and say it with me now, there's got to be an easier way. And then they re-implement it again. And they don't learn from those mistakes. So hopefully Kubernetes is kind of the last one, because at this point it's not patent encumbered. Like VMware sucked because, or Hyper-V sucked because VMware held patents. Patents that Hyper-V couldn't infringe on. So they took a lot of open standards routes. And realistically, because Intel and NVIDIA and VMware were the big ones, AMD and Hyper-V tended to work together, at I guess ATI at the time. You can do really cool stuff with a modern AMD GPU and Hyper-V that costs you $200,000 a year in VMware, and is free with Hyper-V because of open standards and patents. So Kubernetes is the first time we're doing this where it's not patent encumbered. It is actually open. People can actually implement their own use cases if they want to, and then can upstream them and outsource them and open source them to the community if they want to. It's going to depend on a lot on how people actually use the tool and what they actually do with it, because we can put these blocks together in a ton of super cool ways. Bottle Rocket, I'm going to list the vendor here. AWS, it's a hardened container-focused operating system. It's got nothing except just enough, like run C or whatever your container runtime is, to run your containers. And that's it. Kata, it came out of an OpenInfra, Microsoft, and Intel partnership. They've all joined forces and open sourced it. Containers inside VMs. So you can run your containers inside of the same hardware virtualization guarantees you get for VMs. Cool. We're starting to put these together in a way that matters, right? Firecracker, micro VM segmentation. They use this to drive Lambda, their global serverless thing. So you can use Firecracker for containing tiny containers, things that are small to start, small to run, and small to die. KubeVirt, if you want to manage your VMs as Kubernetes objects, you can do it this way. Right, so we talked about Kubernetes is not a container management tool. It just happens to come with it out of the box. You can build whatever you want. There's certificate management there. You could stand up a Kubernetes cluster and just have it issue certificates. That could be the only thing you do with it. You never actually run a workload on it. It can just issue certificates from a hardware certificate authority. Like if you've got a YubiKey HSM you have plugged into a server, you can pass that through to your certificate manager. It does all the signing, and then you can just hand keys out if you want. there's tons of things that we can do with it. We're just kind of choosing not to, right? There's a lot of things that we can do with Kubernetes we couldn't do before easily. Scaling the management plane of VMware was a pain. You had your VMware cluster, but your VMware cluster was the size of the cluster, and scaling it was kind of good and kind of okay and kind of not. And plugins were expensive because they were all VMware, and licensing was a thing. But then we get mutating admission controllers. I lose sleep over that one. You can say, hey, I want to run X. And the control plane says, cool, by X you mean Y, right? So I'm going to turn X into Y, and I'm going to run that. So anyone looking at your cluster goes, why is this here? All right, because Jim from accounting tried to run that Nginx server, so it actually turned it into this. So to the point of logging, whenever you try to blow your own foot off, you should probably keep track of what you use to do it. Right? And the simple air quotes here, I want to come back to the fact that Helm uses Go templating, which is Turing complete. So if you're using Terraform, or if you're using a provisioning server or Ansible or something, and you're using a Helm plugin, and you give it a Helm template, you can run arbitrary code on your provisioning server as part of your template before it even does anything on Kubernetes. So the opportunities for making sure that the stuff you're running is not the Kubernetes equivalent of curl pipe to sudo bash. Like there's versioning, there's package management, there's supply chain that you need to think about when you're deploying a Kubernetes cluster at scale. And the short answer is, don't do more than you need. If you don't need Helm, and you don't need to update the Helm template all the time, you can turn that Helm template into a standard Kubernetes manifest. Helm template. Don't apply it, just give me the manifest. Great, now I can audit the manifest, version the manifest, and I know what I've done. I know what ran. There's tons of stuff here where it's not well documented. It's not clear what problem a lot of this stuff solves because it wasn't really intended to solve a problem. It was intended to do a ton of stuff in a bunch of different ways. So we find ourselves here standing on the beaches of this beautiful ocean. We can go anywhere we want, but really, I just want to sit down. I don't want to get on a boat and jump on a cruise ship and go to Greece and then get off and get lost. I just want to sit somewhere. And that's where I'm at. So.